Good morning. This lesson is for my Integrated 1 class, but before I get started, I want to say I hope that everyone is doing all right out there. I believe this is Unit 5, Lesson 6, but I don't know. It doesn't really matter, but what does matter are the goals. And our first goal is I'm going to tell you a story about Gauss. And then our second goal is we're going to use the concept from the story to solve a system of equations like we've been doing. We've used transitive property, substitution, and we've done graphing. There's another method, and it comes from this story about Gauss. And so Gauss was born in 1777, and he is somebody who we would call a genius, a prodigy, somebody who could do mathematics unlike anybody before him. And in college, I remember walking into professors' office hours to ask for help, and they all had pictures of Gauss on the wall. And so they paid homage to this great mathematician, probably one of the greatest mathematicians. And I want to tell you a story about when Gauss was, I believe, 9 years old. So Gauss lived in a time where only two types of people got to go to school: the rich and the talented. Gauss was not rich, but he was talented. Another story about Gauss was at the age of 3, he found an arithmetic mistake in his father's books. A 3-year-old. Have you ever talked to a 3-year-old, let alone have them do mathematics? A 3-year-old found a mathematical mistake that his father made. But this story is about Gauss when he's 9. Talk to a 9-year-old, I think they like turtles. Anyways, the story about Gauss is the following. He got to go to school, and during the math lessons, he was able to figure out the answers very quickly and the concepts very quickly. And this was very frustrating to the teacher because the teacher had other students to teach. And so Gauss was given busy work by the teacher. The teacher wanted to just give Gauss work to keep him busy. So the teacher would ask Gauss to do these tasks that would just allow him to teach the other students. And so the teacher told Gauss one day, "I want you to add up the first 100 numbers." So this 9-year-old writes out the first 100 numbers like this: 1 plus 2 plus 3, and he can, continues the pattern, and he gets to 98 plus 99 plus 100. This 9-year-old realizes that these numbers must add up to something. Now, when we talk about someone who's a prodigy, who's a genius, they see things that the normal person doesn't see. This 9-year-old looked at this and realized he could create a pattern, and here's how he did it. He reversed the order of the numbers. 100 plus 99 plus 98 plus ... plus 3 plus 2 plus 1. This also equals S, the same sum. But this 9-year-old realized that you could actually, in fact, add the equations together. 9-year-old. And so here we have 1 plus 100, which is 101. 2 plus 99, that's another 101. 3 plus 98, that's another 101. Plus ... 98 plus 3, that's 101. And 99 plus 2, that's another 101. And 100 plus 1, that's another 101. And S plus S, that's 2S. That's twice the amount of what it's going to be. This 9-year-old created a pattern. Remember, we like patterns. He created a pattern from adding numbers together. He also realized that there's 100 101s. And this is equal to twice the sum. And if we divide out the 2, we've actually calculated the sum of the first 100 numbers. It's the amount of numbers you have times 1 more divided by 2. It works for anything. 9-year-old. Now, the point of this story, why I'm telling you this story, and this is the key for the lesson, is the point of this story is we can add equations together. That is the entire point of the Gauss story. We can add equations together. I'm going to go ahead and erase this and set up the second goal. And we will see how we use what this 9-year-old Gauss taught us we could do to solve systems of equations. I'll be back. I'm back. All right, let's go ahead and continue with our second goal, but let's just remember what our story was about that Gauss taught us. Remember, Gauss showed us that we can add equations together, and we're going to use the concept from the story to solve a system. I have the steps written down that we're going to use. Our steps for Gaussian elimination, it's either called Gaussian elimination or elimination. So our first step is to add equations together. Our second step is to solve for the remaining variable using the 6 steps, which we know how to do. And then our third step is to use the answer from the second step in either equation to find the other variable. Remember, these are equations of lines. We're trying to find out where the lines cross. All right, so I have 2 examples, and I picked these 2 examples for very specific reasons. I want to make sure that you guys understand that the problem can go in one of 2 directions. So let me find a marker, and let's get started. There we go. All right, here we go. So we're just going to follow the steps together. We're going to follow the steps that Gauss, 9-year-old Gauss showed us we can do. We can add the equations together. When I add these equations together, my x values cancel, and if I have 6, I owe you 1. Remember, this is minus 1. If I have 6, I owe you 1. I still have 5. So I get 5y is equal to 15. I did step 1. I added equations together. Now our second step is to solve for the remaining variable using the 6 steps. Well, guess what? We only need 1 step to do this, right? I can't eliminate a fraction. I can't distribute. I can't combine like terms. All variables are on one side. I can't add or subtract away a number, but I can divide away a number. So now I'm going to divide away a 5. And y is equal to, 5 goes into 15 3 times. So now I get to pick an equation to plug in and work out. I like the second equation because the numbers are smaller. 3x minus 1y equals 6. My y value is going to turn into 3. So I have 3x minus 1. I put a parentheses in place of the y, and I put a 3 inside there, and that's equal to 6. So I have 3x minus 1 times 3 is minus 3, and that's equal to 6. And again, I have my 6 steps to solve, right? 1, 2, 3, 4, 5, and 6. Can I eliminate fractions? No. Can I distribute? No. Can I combine like terms on either side of the equal sign? No. Can I get all variables to one side? No, they're already on one side. Can I add or subtract away a number? Yes, I can. I can add a 3 to both sides. So here I get 3x is equal to 9, and I'm going to do my last step, which is to divide out the 3, and I get x is equal to 3. I have an ordered pair, and this ordered pair, my x and y value is where these lines cross. So I know these lines cross at 3, 3. Notice on this problem, the x canceled. Okay, notice the x canceled. And I'm sorry I'm blocking. Notice the x canceled. Okay. I was going to ask if there's any questions, but there's no one here. It's just me and the crickets. Let's move on to example 2. And again, we're going to use the steps, the 3 steps to solve. I should add, we use the steps 1 through the 6 steps to find the other value, but that's okay. Let's add the equations together here. (2x and 2x), that's 4x. Minus 4y plus 4y, they cancel. If I owe you 16 and I have 8, you're going to tell me you still owe me 8. Right? Now, notice on this problem, the y's cancel. All right, notice the y's cancel. So sometimes the x will cancel, sometimes the y will cancel. Okay? And now again we use our 6 steps to solve. We only have to use our last step. Divide away. That means that x is equal to negative 8 divided by positive 4. That's going to be a negative. It's negative 2. I get to put this value in either equation, and I like the bottom equation because the numbers are small. So I'm going to replace the x value with a negative 2, and I'm going to have to solve for my y value. So now I get 2, and instead of an x, I put a parenthesis, and inside the parenthesis, I put a minus 2 plus 4y is equal to 8. Again, I plug the x value in here, and I rewrote the rest of the equation. And again, I do my 6 steps to solve. And I wonder if I'm going to do the exact same steps that I did before. Let's actually simplify this. This becomes minus 4 because it's 2 times negative 2. Minus 4 plus 4y is equal to 8. All right, can I eliminate a fraction? No. Can I distribute? No. Can I combine like terms on either side of the equal sign? No. Can I get all y's to one side of the equal sign? Wait. Distribute, combine like terms, get all y's to one side? No. Can I add or subtract away a number? Yes. I can add the 4 to both sides. I think I was going too fast right there and I confused myself. I hope I didn't confuse you guys. I get 4y is equal to 12, and I'm going to divide away a number, and I get y equals 3. So the ordered pair that these lines cross at is minus 2 comma 3. That is the solution. We tend to do Gaussian elimination when the equations are in standard form. It seems to be a simpler way. When you have an equation that y equals, we do substitution or we do transitive. So hopefully you're picking up on the differences of the problems. I'm going to go ahead and end the lesson here. I hope everybody's doing all right. Have a good day, everybody. Bye-bye.